Yeah. Please complete this question first. Which of the following compound gives aromatic, once again, which of the following compound gives aromatic compound in keto-enol tautomerism, right? I have given 1, 2, 3, 4, 5 options. Among these, which is the correct answer? Now come to this first one. If you are using proton from this carbon atom, right? So you can write enol form like this: pi bond, pi bond, pi bond, OH. Is it aromatic compound? Yes, that is aromatic compound, right? Even from here also, by applying what space tautomerism, you will get this compound pi 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 OH, aromatic compound. Again, this is also correct option, right? Here, by default, what is the fourth valency on this carbon atom? Yes, hydrogen. Even though they are not giving hydrogen atom, we can use their hydrogen. Why? Because what is the carbon valency? Carbon valency is 4, right? So by using this proton, you can write enol form like this: methyl pi 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 OH. That is also giving aromatic compound. Next one, yes, this one also giving aromatic compound. Yeah. So how to write the enol form? Use hydrogen from nitrogen atom. Then this is your enol form: pi 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 OH. Yes. And last compound, for this carbonyl I am using hydrogen from this nitrogen, and for this carbonyl I am using from this nitrogen, and for this carbonyl I am using hydrogen from this carbon atom. Then how to write its enol form? Here N double bond OH, N double bond OH, and here OH. Where from you are taking proton? From nitrogen atom. Yes, here you write the double bond, and here also same thing, double bond OH, double bond OH, and here already there is a nitrogen atom, and close the ring system, right? It is also aromatic compound. So all these are correct. A, B, C, D, E. Different types of questions they are giving on the basis of keto-enol tautomerism. Almost all types of questions we are trying to discuss here. Okay, let me go to next example. So in the next example, I am giving this question: write all possible stereoisomers, write all possible stereoisomers when it undergoes keto-enol tautomerism. Yeah, that is the question. And your given compound is like this: C double bond O, CH2, CH2 and CH3. This is the given question. So they are giving one compound ketone. When it undergoes keto-enol tautomerism, you are expecting how many number of stereoisomers. For that compound, you write the enol form. Write all possible stereoisomers of stereoisomers when it undergoes keto-enol tautomerism, right? They can also ask the same question like this: what are the possible stereoisomers of enol form, right? So here, according to this given question, I am writing the enol forms like this by using protons. Here left side, yes, acidic proton is present. Right side also acidic proton is present. By using both protons, we can develop and we can write that enol forms. Yes. What is the first one? You look at this enol form. I am using proton from left side. Yeah, from this carbon atom. Okay. And what is the result here? You can write like this: double bond OH. Double bond OH. Here as it is, you write like this: CH2, CH2 and CH3. And what is the fourth valency of this carbon atom? Hydrogen. Now same thing you can represent like this: CH2, CH2, CH3. Again here OH group, but here I am writing methyl downside and hydrogen upside. Same molecules, just I am changing position of methyl and hydrogen. I am changing position of methyl and hydrogen. You are getting new stereoisomer. Okay, fine. CH3. These are the two molecules. By using left side proton, you are getting two molecules, two stereoisomers. Here you don't write any cis trans and EZ nomenclature like that. Just you write the geometrical isomers. We know that here optical isomers are not possible. Why? Because there is no asymmetric center in the enol form. Just we are considering only geometrical isomers. For example, if you are using right side proton, then what is the result here? This is the result. OH, you write like this and introduce double bond between these two carbon atoms, and one group is ethyl and one is what? Hydrogen. And same molecule we can write like this. Here I am not going to change left side groups. Right side, here on this carbon atom I am taking hydrogen up and ethyl downside. These are the possible ways of writing enol forms with the different stereo isomers. Now here totally how many forms are there? First form, second and third, fourth. Okay, these are the maximum possible stereo isomers. This is also one type of question from keto-enol tautomerism we can expect. So they are giving any kind of like keto form and they are asking enol forms, and here the question is how many number of enol forms are there in the given compound. Total number of stereoisomers of enol form. So total number of stereoisomers, total number of stereoisomers of enol form equals to how much? 4. Very important question. For example, on the basis of same question, if they are giving like this C double bond O, CH2, CH3, this is the given question. How many number of geometrical isomers are possible? Number of, right, same thing, number of geometrical isomers of enol form. Yeah, this is the question. Number of geometrical isomers of enol form. First one, if you are selecting proton from left side CH, then what is the result here? OH, right side CH2 and CH3. Now, is there any chance for geometrical isomerism? There is no chance for geometrical isomerism. What is the reason? On this carbon atom, here 2 hydrogen atoms are there. That is not satisfying condition for geometrical isomerism. That enol form not showing that geometrical isomerism. Okay, no problem. Then try with right hand side carbon atom. Here hydrogen atom is there. Fine. If you are using that hydrogen atom, then how to write enol form? Here you write the pi bond. Next one, OH and CH3. What is the fourth valency? Yes, it is hydrogen. Clear. And same thing, same as previous. Here around the double bond, I am not going to change position of this OH and methyl group. Okay. Right side methyl and hydrogen atoms are there. These two groups I am exchanging like this, hydrogen and this methyl group. These two are the two different geometrical isomers. Then what is the answer? 2 geometrical isomers are possible. Clear? Fine. 2 geometrical isomers. There are a lot of ways to ask the question on keto-enol tautomerism. Yes, let me go to another example. Here this is the given molecule, ketone is given and CH2, CH3. Same thing, how many geometrical isomers are possible in enol form, right? And what is the specialty of this molecule? Left side and right side hydrogen atoms are equivalent. You can use either from left side or from right side. Okay, only one side now we are using right. For example, if you are using from left side, then what is the result here? Here I am writing like this, OH, CH2 and CH3. Fourth valency is hydrogen atom. Enough. And again same thing, you can fix any 2 groups, no restriction, but here I am taking right side groups at fixed position. I am trying to exchange CH3 and hydrogen. So what is the group here? I am taking CH3 and upper position hydrogen. These are the 2 compounds. Okay. How many geometrical isomers are possible? 2 geometrical isomers. Number of geometrical isomers equals to 2. For a given compound, how many number of geometrical isomers are possible in enol form? Our answer is 2. This is one kind of question. Okay. Sometimes they are giving which of the following compound gives highly unstable enol form, and sometimes which of the following compound gives aromatic enol, and sometimes how many geometrical isomers are possible in enol form. These are the different types of questions, right? Let us try one more example. Yeah. Here our question is, ketones are what given? 1,3 diketones. This is my first compound, double bond O, double bond O. In the first compound they are giving combination of 2 6-membered ring systems, Next one, in the second compound they are giving ketone and right hand side 5-member ring system with C double bond O. This is our second compound. And let us come to third compound. Here two 5-member ring systems are what given, C double bond O, again C double bond O. Here question is, among the given compounds, which one giving more enol content? Yeah, that is the question. Which among the following giving more enol content? That is our question. Yeah, very good question. On the basis of a bond angle strength, we are going to solve this problem. Okay, what is the common feature in all these three compounds? Where from we are selecting proton? Yes, from this carbon atom. Why? Because it is placed in between two electron withdrawing groups. Here also same thing, two electron withdrawing groups. Okay, yeah, that is our acidic CH or acidic hydrogen. Whenever hydrogen is connected with the carbon atom and which is planked between two electron withdrawing groups, that should be taken as what? Now more acidic. Now here two possibilities are there. Now you can take double bond either from left side or from right side. Here conveniently I am taking like this OH and C double bond O. You can take same double bond left side also, there is no problem. This is the enol form. And here two options are there, left and right hand side. But which is better? Definitely left side pi bond is better when compared to right side. Here I am taking like this OH and C double bond O. Yes. Next one, here there is no chance either from left side or from right side. There is no difference, both giving what? Same type of enol form. Yes, this is our compound. Okay. Now you check for stability of this compound. Yes. In first one, yes, there is a intramolecular hydrogen bond also. Second one also, it is having intramolecular hydrogen bond. But what is the difference between these two? Now you look at this carbon atom here. What is hybridization? sp2 hybridization. At this carbon atom, hybridization sp2. And here at this carbon atom, what is hybridization? Same, sp2. Again here also sp2. Okay. So whenever ring size is less. So now whenever ring size is less and hybridization is sp2, now just you look at this 5-membered ring carbon atom. What is the hybridization? sp2 hybridization. So once sp2 hybridization is present, what is the required bond angle? Required bond angle should be 120 degrees bond angle. So whenever ring size decreases, the bond angle strain increases. Ring size decreases, bond angle strain increases. So from 1 and 2, which is suffering from more bond angle strain? Here sp2 carbon atom, but right hand side, what is the ring size? 6-membered ring. Yes, that is also having some strain, but somewhat better when compared to second compound. In the second compound, here this carbon atom is part of 5-membered ring system. Once the ring size decreases with sp2 hybridization, bond angle strain increases and stability decreases. This molecule is suffering from more bond angle strain when compared to first one. Okay, right. Here both the rings, this is the common carbon atom for these two ring systems. What is hybridization? sp2 hybridization. Now both rings are suffering from bond angle strain. That's why among these three, A, B, C, A giving more enol content when compared to B, B is better than C. Okay, this is the order. Now A giving more enol content than B, next one C. That is the decreasing order of giving enol content on the basis of bond angle strain. Okay, next I am going to explain what are the factors affecting keto-enol tautomerism. Factors affecting keto-enol tautomerism. Okay, factors affecting keto-enol tautomerism. So what are the general factors which are affecting keto-enol tautomerism? Let us start from temperature. First one I am taking, what is the effect of temperature? How that temperature is affecting on keto-enol tautomerism, right? So to explain effect of temperature, I am taking 1,3 dicarbonyl compound. This is very good example. 1,3 dicarbonyl compound. So what is the name of this form? We know that this form is keto form. And what is the enol form of this compound? Yes, C double bond O. Here double bond I am taking. Next one OH, and it has intramolecular hydrogen bond. Yes, intramolecular hydrogen bond. Clear. One is keto form and one is enol form. Okay, right. So what is the effect of temperature? Basically, this hydrogen bond is weak when compared to what covalent bond. It is affected by temperature. Here, by increase in temperature, breaking of hydrogen bond takes place. Breaking of hydrogen bond takes place. Breaking of hydrogen bond takes place. That is the effect of temperature. Okay, there is no problem with other bonds, but because of weak bond, hydrogen bond, yes, that is the stabilizing factor. But by increasing temperature, so breaking of hydrogen bond takes place. Once if there is a breaking of hydrogen bond, slowly what about the enol content? Decreases or increases? Enol content slightly decreases. Okay, compared to normal temperature, if you are increasing water temperature slowly, because of breaking of hydrogen bond, enol content decreases. Okay, you write the same point. By increase in temperature, slowly enol content decreases. Just remember that point. Okay, enol content decreases. That is the effect of temperature on keto-enol tautomerism. By increase in temperature, breaking of hydrogen bond takes place, and by increase in temperature, slowly enol content decreases. Clear? Any doubt? Fine. Next, we are going for solvent effect. So, what is the effect of solvent in keto-enol tautomerism? Yes. Next one, effect of solvent. Effect of solvent, right? Now, in case of effect of solvent, again I am going to take same 1,3 dicarbonyl compound, right? 1,3 dicarbonyl compound, double bond O, and I am taking enol form also, right? Double bond O here, double bond, next O and H. This is our keto form. Okay, right? Sorry, enol form. Right side enol form, left side keto form. I am taking like this one keto form, and this one enol form. What is the effect of solvent? Now, for example, if I am taking polar solvent, I am going to take polar solvent. What is the best example for polar solvent? Best example for polar solvent is water. Very good example, right? So, what is happening in presence of polar solvent? Now here, first I am taking here, come to keto form. Here, just you compare electronegativities difference between carbon and oxygen atom. Which is more electronegative? Oxygen is more electronegative than carbon atom. That's why I am giving partial positive charge to oxygen atom and partial negative charge to oxygen and partial positive charge to ketone. Next one, partial negative charge and partial positive charge. And what is the solvent we are using here? Polar solvent. Okay. So because of using that polar solvent, we know that water molecule shows permanent dipole moment and it is considered as polar. What is the use of this polar solvent? Yeah, it has delta plus hydrogen, delta plus oxygen, delta minus hydrogen, delta plus. Yeah, delta minus, delta plus, delta minus, delta plus and plus. Delta nothing but partial positive charge and partial negative charge. Now here this water molecule is solvating this negative charge. Your carbonyl compound in keto form, that is highly solvated with the polar solvent. Like that, here also water molecules are solvating. Same water molecules I am using here H2O, and we know that delta plus, plus and minus, partial positive and partial negative. So here these particles are solvating that carbonyl function. So like that, lot of water molecules are there in the solution. All these water particles are greatly solvating that keto form, right? But in case of enol form, two free carbonyls are not there. sorry, in enol form. In enol form, there are no free carbonyls, but in case of keto form, yes, there are free carbonyls. This is very important point. Solvent effect changing percentages of keto and enol form at equilibrium in presence of polar solvent. Okay. Now, if you are asking what diketone, 1,3-diketone, now it will say that yes, I am more and more comfortable in polar solvent. Why? Because I am more solvated by the water particles. That is the advantage. Because of that advantage, because of greater solvation of that 1,3 dicarbonyl compound, this dicarbonyl compound wants to stay in keto form when compared to what enol form. So in that case, keto form is more dominating when compared to that enol form. Very, very important. For example, gas phase molecules are what given. There enol form is better than keto form. So we are going to solve one question on the effect of polar solvent, no problem. Now just you remember like that, your 1,3 dicarbonyl compound is more and more compatible in polar form because of more solvation by water particles. Okay, that's why in presence of polar solvent, keto form is more dominating when compared to enol form. And what is the equilibrium constant value here? Equilibrium constant value less than 1, right? Now you write same point. In presence of polar solvent, in presence of polar solvent like water, in presence of polar solvent like water, keto content is more, keto content is more than enol content, keto content is more than enol content due to greater salvation by water particles or solvent particles. Yeah, this is the point. Very, very important. Just you check once whether it is given in gas form or solution form. If polar solvent is given, keto form is more content when compared to enol form. And what is the equilibrium constant value? Equilibrium constant value is less than 1. That is the effect of solvent. Okay, temperature effect completed, and next this solvent effect is completed. So on the basis of that, now we can write one question. For example, here 1,3 dicarbonyl compound is given like this, C double bond O, again C double bond O CH3, and right hand side we are giving enol form, C double bond O, yes, here OH. These are the two compounds, keto and enol form. Here solvents they are giving what is the solvent given? Polar solvent, water is given. Second condition, liquid solution given, simply in the form of liquid solution, and N-hexane solvent, next one gas phase. These are the 4 different conditions. Here I am taking, okay, again no need to write that solvent, just you observe that. So in what conditions we are taking keto form and enol form? Keto and enol form we are taking in water solvent or simple liquid solution, these molecules itself present in liquid form. And what is the solvent here? N-hexane, and last case gas phase. Here almost around here like 86% around, and here 65%, next one 38% and 24%. So what we observe, in presence of polar solvent, what is the keto content? More or less keto content is more. What is the reason? Because of greater solvation by water particles. That's the advantage. Because of that reason, that molecule wants to stay in keto form when compared to enol form. Okay, yes, 86%. And what about remaining percent here? Remaining around 14% in enol form, and liquid solution 65%. And what about remaining percent? 35%. Next one 38%. And what about here remaining 62%, and here 76%. Okay, you observe these 2 points. In case of polar solvent, which is more dominating? Keto form. But in gas phase, which is enol form. That is the difference. That is the effect of solvent. Yes. Yeah, I am going to next example. For example, question is given like this. This is our question. Here 2 compounds are what given. C double bond O and C double bond O. One second. Yeah. Question is, which among the following compounds, which among the following compounds gives more enol content? More enol content. That is the question. Here options they are giving like this. Now this is our first option. Yes, 1,3 dicarbonyl compound. And second option, they are giving aromatic ring systems like this. C double bond O, again C double bond O, 1,3 dicarbonyl compound, right? And C option, C double bond O. Next one here, ester functional group is given C2H5OH. And fourth option, they are giving like this, 4-member ring system. Here C double bond O. That is the given question. Which among the following compounds gives more content of enol form? What is the right option? So we know that fourth compound giving highly unstable compound. How to write that enol form? This is our enol form. So what is the problem with this molecule? It is anti-aromatic compound. Anti-aromatic compound. Okay. So that is highly unstable anti-aromatic compound. When you compare A, B and C, already these examples are completed because of intramolecular hydrogen bond and greater extended conjugation. Now this one exists more in enol form when compared to keto form. This compound gives more enol content. More enol content. Yeah, very good question. So this is the story about keto-enol tautomerism. And finally, before going to close this keto-enol tautomerism, last concept, what is kinetic isotopic effect? Kinetic isotopic effect. Kinetic isotopic effect. Here we are discussing about deuterium exchange with hydrogen. Okay. Kinetic isotopic effect. So what is the kinetic isotopic effect? So to understand kinetic isotopic effect, I am giving one simple example, HC double bond O CH3. Here how many alpha hydrogen atoms present? It has 3 alpha hydrogen atoms, or we can say that 3 acidic hydrogen atoms, or I am taking like this, 3 alpha hydrogen atoms, all are acidic in nature, 3 alpha hydrogen atoms. What is the nature of that hydrogen? Acidic or not? Definitely, if that CH is presented alpha position to carbonyl functional group, definitely it acts as what? Acidic in nature, right? 3 alpha hydrogen atoms are there. Here I am going to take one condition that in presence of what? Base. In presence of base, but here in place of hydrogen I am taking deuterium to replace hydrogen atoms by deuterium, and instead of water molecule here I am taking heavy water, D2O. So what is the expected product here? Expected product is like this, HC double bond O. Before taking that condition, how many hydrogen atoms are there at alpha position? 3 alpha hydrogen atoms are there. But on long standing, that is also very important condition, on long standing, all these hydrogen atoms are replaced by deuterium. That is what we call kinetic isotopic effect. On long standing, whatever the number of acidic hydrogen atoms present, all these acidic hydrogen atoms are replaced by deuterium. Okay, right. What kind of questions they are giving on the basis of kinetic isotopic effect? So what is the molecular weight difference between reactant and product? The kind of question coming from kinetic isotopic effect. Here first type of question, type 1, just I am giving type of questions here. Type 1 question. What is the type 1 question? How many hydrogen atoms are replaced by deuterium atoms? That is the first kind of question. On kinetic isotopic effect, now 2 different types of questions are there. First one, how many hydrogen atoms replaced by now deuterium atoms? What is the second type of question? What is what is molecular weight difference, molecular weight difference between, what is molecular weight difference between molecular weight difference between reactant and product, yes. These are the two different types of questions we are expecting from kinetic isotopic effect. What is the first question? How many hydrogen atoms are replaced by deuterium? And what is the second question? What is the molecular weight difference between reactant and product? Now here among the hydrogen isotopes, now hydrogen, deuterium and tritium, what is the mass? 1, 2 and 3. H11, H12 and H13. What is the mass number of this proton? 1. What is mass number of deuterium? 2. What is the mass number of tritium? 3. Okay. So from that you can calculate molecular weight difference between reactant and product. Okay, right. So now what is the mechanism for this reaction? Write the mechanism. After that I will tell you shortcut method. Mechanism. What is the mechanism and how all hydrogen atoms are replaced by deuterium? Okay, right. First you start from this example. C double bond O CH3. It has 3 hydrogen atoms at alpha position. And what is the condition we are using? Yes, base in presence of heavy water OD minus and D2O. From that first OD minus, you start reaction with OD minus. What is the nature of that OD minus? It is acting as base or not? Yes, it is acting as base. What is the meaning of base? Base nothing but it wants to form bond with proton. In the given reactant molecule, where is acidic proton present? From left side or from right side? Yes, from right side there is a acidic proton. That OD minus is searching for proton and simply that OD minus is receiving proton from that carbon atom. So whenever that OD minus is receiving proton from that carbon atom, then what is the result here? Hydrogen and hydrogen. Now that hydrogen leaving 2 electrons at carbon atom, your result is carbon ion. And what will happen in the next step? In the next step, here this carbon ion is interacting with now heavy water D2O, and that is receiving deuterium from this water particle, heavy water, not simple water, that is heavy water, right? H, C double bond O, C, H and H, and here one hydrogen atom is replaced by deuterium. So like that, with the same mechanism, all hydrogen atoms are replaced by deuterium. Same mechanism, same as first step. Okay, again just to remove the proton and introduce deuterium, remove hydrogen, again introduce deuterium, like that. So this is the outline steps of this corresponding process. Here what we are doing here, we are taking base in presence of heavy water. Base is receiving proton from that carbon atom. Yes, now carbon ion formation, and again this carbon ion is interacting with this deuterium. Now that is giving deuterium in place of hydrogen atom. Like with the same mechanism, all hydrogen atoms, any number of acidic hydrogen atoms are present. Yeah, you can take, no problem. All hydrogen atoms are replaced by deuterium. Okay, right. Yeah, this is the mechanism. Write down this mechanism. Then after that, I will give you examples. If you are able to identify number of acidic hydrogen atoms in the given compound, then we can solve this problem. Right. Identify replaceable hydrogen atoms in kinetic isotopic effect of ketoenol tautomerism. Otherwise, just to write this question, identify in kinetic isotopic effect. Identify replaceable hydrogen atoms in kinetic isotopic effect. Yeah, you start from this example. CH3. Next one, C double bond O, CH3, CH2, CH3, like that. Just you identify number of acidic hydrogens, then that is the right answer. And here you select cyclohexanone, very good, and cyclohexanone with the methyl group one side, cyclohexanone, two methyl groups, one left side and one right side, okay. And here you write this example, cyclohexanone, both sides methyl groups are there. And another example, C double bond O and C double bond O. These are the given molecules. Identify number of replaceable hydrogen atoms by deuterium. Now come to this first example. How many acidic hydrogen atoms present here? 1, 2, 3, 4, 5, 6. On long standing, now according to the previous mechanism, all hydrogen atoms are replaced by deuterium. Then what is the answer here? C double bond O, C D3, again C D3. Yeah, this is the answer. How many replaceable hydrogen atoms? 6 replaceable hydrogen atoms are there. Next one, when you come to second molecule, here left side 2 hydrogen atoms, right side 3 hydrogen atoms are there. Hydrogen, hydrogen and hydrogen. How many replaceable hydrogen atoms? 5 hydrogen atoms are replaced by deuterium. 5 hydrogen atoms are replaced by deuterium. 5 hydrogen atoms are replaced by deuterium. Okay, fine. By deuterium. 5 hydrogen atoms are replaced by deuterium. Next one. In the next question, how many replaceable hydrogen atoms? Again and again I am not going to write that statement. Just to identify number of hydrogens. 1, 2. Again here also 1, 2. Total how many hydrogen atoms? 4 hydrogen atoms. 4 replaceable hydrogen atoms are there. In this example, from left side hydrogen, from right side hydrogen, hydrogen and hydrogen. How many replaceable hydrogen atoms? 4. Next one, from left side 1 hydrogen, from right side 1 hydrogen. How many replaceable hydrogen atoms? 2. 2 hydrogen atoms will be replaced by deuterium atoms. And here from right side hydrogen, hydrogen, from left side hydrogen and hydrogen. On long standing, all these 4 hydrogen atoms are replaced by deuterium. Okay, right. And next molecule, hydrogen and hydrogen. Here hydrogen. How many replaceable hydrogen atoms present? 3. Here from right side 1 hydrogen atom, left side 1 hydrogen atom. How many replaceable hydrogens? 2. 2 replaceable hydrogen atoms are there. And in this molecule, is there any replaceable hydrogen atom? Is there any replaceable hydrogen atom in this example? No. 0. 0 hydrogen atoms are replaced by deuterium. And here with respect to this carbonyl, there is a hydrogen and hydrogen. Yes. Left side also hydrogen and hydrogen. Right side 1, 2, 3 and 4. With respect to upper carbonyl, 4 hydrogen atoms are there. With respect to lower carbonyl, 4 hydrogen atoms are there. Total 8 hydrogen atoms are replaced by deuterium. 8 hydrogen atoms are replaced by deuterium. Very simple question. Yes. Next important examples. Yeah. This is the given question. Double bond O, again double bond O, right? For example, same question given like this. Double bond O. Here. One second. Be better to start from acyclic conjugated systems like this. Yeah. First complete this question. Here how many alpha hydrogen atoms present? Number of acidic hydrogen atoms. Here number of acidic hydrogen atoms. Yes, between these two, hydrogen and hydrogen. Here hydrogen, hydrogen. Yes, next one hydrogen and hydrogen. Total how many hydrogen atoms? 6 hydrogen atoms are replaced by deuterium. Next one, this is very important example. Left side on sp3 carbon atom, there is no hydrogen. Here simple hydrogen atom is present, right? This is the hydrogen directly connected to carbonyl. From right side, where from we are selecting acidic proton. That's very important. You remember this point, HC double bond O, double bond and CH3 given. Very important example. First of all, identify acidic hydrogen. This is the acidic hydrogen atom. Okay, acidic hydrogen atom. For example, if you remove proton from that carbon atom, then what is the result here? Result you are getting carbanion. So this carbanion is interacting with heavy water and that carbanion is receiving deuterium atoms. And what is the second possibility? And sometimes now we can write one example with deuterium like this, CD, remaining hydrogen atoms. Just to remember this point. So wherever carbanion appears, there deuterium should be connected at the end of the reaction. Now come to this one. Here we can write resonance forms like this, shifting of pi electrons and negative charge, C double bond O and here double bond negative charge. Here also we can introduce deuterium. That is very important point. So wherever carbanion appears, there finally deuterium atoms are connected to the same carbon atom. So now every time there is no need to write the mechanism. I am going to give one shortcut method. Right? Now you start from this carbon atom. What is hybridization of that carbon? sp2 hybridization, right? And this is our second carbon atom, same hybridization sp2. Third carbon atom sp2. And come to fourth. Better to give numbering like this. Always you start from carbonyl carbon atom 1, 2, 3, 4. For example, at fourth carbon atom, acidic hydrogen atom is present. All these acidic hydrogen atoms are replaced by deuterium. First condition. I am writing product like this, C double bond O. Next one second. HC double bond O. This is the shortcut method. First one here, all hydrogen atoms are replaced by deuterium. Remember one important point. At even number of carbon atoms, if there is a chance for extended conjugation, pi, sigma like that, if you are producing carbon ion here, that hydrogen atom is replaced by deuterium. Whatever the hydrogens present at fourth carbon atom, all hydrogen atoms are replaced by deuterium. In addition to that, at even number of carbon atoms, even though that hydrogen atom is present on sp2 carbon atom, that is also replaced by deuterium. What is the reason? This is the reason. So wherever carbanion appears, at each carbanion we can introduce deuterium atoms, right? For example, if you are going to identify number of replaceable hydrogen atoms in the third compound, here what is the answer? Total how many hydrogen atoms replaced by deuterium? 4 hydrogen atoms are replaced by deuterium. Come to this molecule, third one, here CH3. There is no doubt with these hydrogen atoms. All these hydrogen atoms are replaced by deuterium. After that I am giving like this 1, 2, 3 and 4. Don't go for fifth carbon atom. Why? Because if you generate carbon ion at fifth carbon atom, there is no conjugation. Negative sigma, again sigma, there is no pi. No conjugation from fifth carbon atom. Yes. At fourth carbon atom, acidic hydrogen atoms are present. And how many acidic hydrogen atoms are there? Here 2 acidic hydrogen atoms. And in case of deuterium exchange, we can also take hydrogen from second one. Just I am taking only even number of carbon atoms, second carbon and fourth carbon atom. So totally how many replaceable hydrogen atoms are there? From left side 3, from right side 4, 5, 6. Totally 6 hydrogen atoms will be replaced by deuterium. Clear? Yeah. I'm going to give some more examples on deuterium exchange. Yes, this is the given 6-member ring system. Yes, double bond O, right? And here C double bond O CH3 like this. Yeah, next example. This one. Try these questions. Identify number of replaceable hydrogen atoms. How many number of replaceable hydrogen atoms? Yes, you can select from this carbon atom without any confusion 2 hydrogen atoms. Clear? And just you look at left side, there is a conjugation. You start like this: 1, 2, 3, and 4. At 4th carbon atom, how many hydrogens present? 2 hydrogen atoms are there, like this: hydrogen and hydrogen. Already we know that if there is a conjugation, if you are going to generate carbene at 4th carbon atom, now here 2nd carbon hydrogen atom also replaced by deuterium. Yes, totally how many hydrogen atoms? 1, 2, 3, 4, 5. 5 hydrogen atoms are replaced by deuterium. Clear? Come to next example. No doubt, left side CH3, all these hydrogen atoms replaced by deuterium. And here you start numbering like this: 1, 2, 3, 4. Here I am taking 4. 1, 2, 3. Next carbon 4. Next carbon again 4. Yeah. Is there any hydrogen at 2nd position? No hydrogen. At 4th position, how many hydrogen atoms present? According to the carbon valency, 3 hydrogens are there. And here, how many hydrogen atoms? Yes, 2 hydrogen atoms are there. Now, totally how many replaceable hydrogen atoms? 3, 4, 5, 6, 7, 8. 8 hydrogen atoms are replaced by deuterium. Next example, no confusion. One second. Yeah. I am taking like this: 1, 2, 3, 4, 5, and 6. Very good example. So if you are taking from 6th position, how many hydrogen atoms are present? 2. And don't forget hydrogen from 2nd position and 4th position also. From 4th and 2nd position. Why? Because there is a conjugation from left side. Totally how many replaceable hydrogen atoms? 1, 2, 3, 4. 4 hydrogen atoms are there. Number of replaceable hydrogen atoms. All these are replaced by deuterium. Yes, here 1, 2, 3, 4. 1, 2, 3, 4. 1 second. Here you write methyl group. Just to simplify the problem. Yeah. Now you can continue. 1, 2, 3, 4. At 4th position, how many hydrogens present? 2 hydrogens. And here, what's happening? 2nd carbon and 3rd carbon atom. At 2nd position also, 1 hydrogen atom is present. Totally how many replaceable hydrogen atoms? 3 hydrogen atoms are replaced by deuterium. Now here I am going to write the product. Okay. Here also I am taking methyl group. Next one here also methyl group. Yeah. Here, what is the product? I am writing product also. Yes, at this carbon atom, 1 hydrogen atom is there, that is replaced by deuterium. Right side, I am taking double bond. Here 1, 2, 3, and 4. 2nd position also replaced by deuterium. So 2 hydrogen atoms are replaced by deuterium. Yes. Now tell me last one. Is there any replaceable hydrogen atom? No hydrogen is replaced by deuterium. If replaceable hydrogen present at 4th position, then we can also use at 2nd position. But here there is no hydrogen atom. There is no replaceable hydrogen in the given compound. Okay. Few more examples I am giving on the basis of deuterium exchange. Here you write the products also. For example, compound is given like this: bridged compound is given. C double bond O. Carbonyl functional group is presented bridged position. Here C double bond O given at non-bridged position. Another example like this. Yes, C double bond O, methyl and methyl, next compound. And another example. OH 5-member ring system. 1 second. Let me write clear. Molecule. 6-member ring, and this one 5-member ring system. Here carbonyl is given, here also carbonyl, and here OH is given. Just you complete these 4 examples, then yeah, come to first molecule. Carbonyl functional group is there, and here alpha hydrogen atom is present, but alpha hydrogen atom is present. Is it possible to use these hydrogen atoms in keto-enol tautomerism? No. Why? Because they are present at bridgehead carbon atom. You are not getting stable enol form. So here simply write like this: no replaceable, or you write like this: no deuterium containing compound. You are not getting compound with deuterium. That means no hydrogen atom is replaced by deuterium. Okay, right. Come to next example. Here we have 2 possibilities: hydrogen from bridgehead position next to 2 hydrogen atoms from here. Then what is the result? We are not using this hydrogen atom. Why? Because that is present at bridgehead position. Yeah. So just these 2 hydrogen atoms are replaced by deuterium. 2 replaceable hydrogen atoms are there. Now come to this example. Here there is no chance from this carbon atom, and even though hydrogen present at bridgehead position, we are not using. No deuterium containing compound. No deuterium containing compound. Yeah. Come to this example. Here carbonyl functional groups are there. Here you can select 2 hydrogen atoms from this carbon. Again from here, 2 hydrogens. From here 2 hydrogens, and OH also giving acidic hydrogen. That means what about your product? This is our product. Yeah, I am writing O, and for writing deuterium I am using different color. 1 second. Yeah, this is my carbonyl. Again carbonyl. Yes. Now these are the 2 hydrogen atoms. Again 2. 1 second. Let me write deuterium. OD minus D2. This is the common condition for every reaction. I forgotten giving that condition, right? Okay. Here deuterium. Actually we started with deuterium exchange, no problem. These are the replaceable deuterium atoms, and one more possibility is there from this OH. Totally how many hydrogen atoms replaced by deuterium? 1, 2, 3, 4, 5, 6. 6 hydrogen atoms are replaced by deuterium. Any type of question they can give. First one, number of replaceable deuterium atoms, number of replaceable hydrogen by deuterium. Okay, right. And what is the molecular weight difference? And third question they can give, in the given reaction condition, how many deuterium atoms now observed in the final resulting product. These are the different types of questions. Last question I am giving. Question: total number of deuterium atoms present in the compound. What are the total number of deuterium atoms present in the compound? That is our question. You write like this: double bond O. 1 second. Little more complicated example I am giving. This is the given molecule. Now, if you start numbering like this 1, 2, 3 and 4. At fourth position, there is a acidic hydrogen atom. Then how to write? But in this direction 1, 2, 3, 4. Here there is no acidic proton. That's why not possible to replace hydrogen from left side. Here how to write the final resulting product? Pi bond C double bond O. Next one here double bond. And what are the positions for deuterium? Here you can take 1 deuterium. Next one here CH3 in place of 3 hydrogen atoms. In place of 3 hydrogen atoms, you will get 3 deuterium atoms. CD3. So according to the given question, how many number of hydrogen atoms are there? Sorry, how many number of hydrogen atoms replaced by deuterium are in the given compound? Total number of deuterium atoms present in the given compound. What is the answer? 4 deuterium atoms present in the product. Here you write the product in the product. Yeah, question. Total number of deuterium atoms present in the product. How many number of deuterium atoms are there? 4 deuterium atoms are present in the compound. Okay. Now last example, now very important example. Here I am giving like this C double bond O and here double bond is given. Very important example. Whenever this is the position of double bond, just I am taking like this alpha, beta and gamma position. If pi bond is present between beta and gamma, there is no conjugation. But under these conditions, O, D minus and D2O, your compound is undergoing pi bond migration like this, just in order to give stable compound. Pi bond migration. Here what is the product? Alpha beta unsaturated carbonyl compound that you are getting first before deuterium exchange. Alpha beta unsaturated carbonyl compound. Okay. So after alpha beta unsaturated carbonyl compound, now there are replaceable hydrogen atoms. From left side you can take 2 deuterium, and here in place of hydrogen deuterium and deuterium, and here also deuterium. This is the final resulting product. Remember this example, whenever beta gamma unsaturated carbonyl compound is given, it undergoes pi bond migration. What we are getting? Alpha beta unsaturated carbonyl compound. Okay. So these are the examples for tautomerism. In the next video lecture, we will discuss about the PYQs. Okay. Thank you.